So today we are gonna talk about the limitations, the limitation of dimensional analysis. Even if I say it's a god tier skill to know how to do dimensional analysis, it does have some limitations, sadly. So sad. But dimensional analysis, if you're good in dimensional analysis, you are very skilled. It's a very easy skill, but you are skilled because it is very useful. So following are the limitations of dimensional analysis. Let's make it a white color. Why not? Because it will stand out. So now let's see a few limitations. So the first one is it does not give information about the dimensionless constant. So if you remember, when we found relations between various physical quantities, we actually did not know the value of dimensional constant. What we know is experimentally we could find it, but we did not know by using dimensional analysis. So this is a big drawback or limitations. So the second one is we cannot derive formula containing trigonometric function, exponential function, and logarithmic function, etc. So these are trigonometric function, meaning sine, cosine, tan, cotangent, etc. Those functions, because trigonometric function, exponential function, and logarithmic function are actually dimensionless because they just give numbers. Exponential function is something raised to the power, so 2 to the power 4, 2 to the power 7, e to the power x. Those are exponential function. And finally, logarithmic function is we will talk about logs in the next video, not the next video, but in some video. So now let's move on to the third one. So basically what you have to understand are trigonometric function, exponential function, and logarithmic function do not have dimension because they give number as a output. That's why we can't derive formula containing trigonometric function. I mean, you can derive it, but you won't see the trigonometric function in the derived expression. For example, if there is a formula called f equals to qbv sine theta. So let me write it. So f equals to qvb sine theta. So if you actually derive this by dimensional method, you will get f equals to qvb. Since q has a dimension, v has a dimension, b has a dimension, but since sine theta does not have a dimension, you won't get sine theta in your result, which is actually wrong. Actually you will get k over here, but k is a constant. In this case the k should be 1, and it's not sine theta because k is a constant and sine theta is actually something that changes. So that's what I'm trying to say. And the third limitation of dimensional analysis is actually the exact form of relation cannot be developed when there are more than one part in any relation. So to explain this, think of the v is equals to ut plus 2as. This sorry, v is equals to u plus at. How the hell did I write that? Like, how the hell did I mess up that bad? Okay, so here if you see v is equals to u plus at, this is a dimensionally correct as well as a physically correct relation. But if you try to derive it dimensionally, you can't get that. You will be very stuck if you try to find this by dimensional method. It's because there is a plus over here. So if there are more parts, you can't actually do it. So try to do it. If you try to do it, you will not get this result. So you will get another form. So that's why the exact form of the relation cannot be developed. I mean, you can get close, you can get v is equals to u or v is equals to at, but you're not gonna get v is equals to u plus at. So if you said the final velocity depends on the initial velocity, you will get v is equals to u. And if you said velocity depends on the acceleration and the time taken, you will get v is equals to at, but you will not get v is equals to u plus at. That's why if there are more than one part in a relation, you can't get the exact form of the relation. I mean, you can get a special case, but you won't get the exact form. So the next limitation is it gives no information. It gives no information whether a physical quantity is scalar or vector. So scalar does not have a direction, vector has a direction. That's basically it. So if you remember velocity has a formula of displacement over time, and speed has a formula of distance over time. So if you do it dimensionally, you will always get this result. So even though you were trying to find the relation of velocity, you will get this result. So in this case, you don't exactly know if it's a scalar or a vector, because even when deriving of velocity, you will still get d by t. So that's why it gives no information whether the physical quantity is either scalar or vector. So now the fifth one is, if a quantity depends on more than 3 factors having a dimension, the formula cannot be derived. Think about it this way. Suppose we had a relation. Suppose I would say let's say gamma is equals to x to the power a, y to the power b, z to the power c, and let's do it this way. Let's say this is x, and let's put capital ABC, capital A, capital B, capital C, capital D raised to the power D. If you had a relation like this, you can't actually derive the formula, because when you will be comparing from this side and this side doing dimensionally, you will get very complex relations. So one can be a plus b plus c equals to 0, b plus c plus d equals to -1, etc., etc., which would give you multiple values that will satisfy the equation. So there will be multiple values of a, b, c, and d which will satisfy the equation. That means you will have a big time choosing which one is the correct one. I mean, there is the correct one somewhere in there, but you can't be sure. That's why the formula cannot be derived, because there are multiple choices and each choice is equally possible, but you know that only one of them is true. So with this, that's it for today's video, and in the next video we are gonna do some questions. So that's it. Bye bye.